Every physical structure in the universe is under constant assault by kinetic energy. Strictly defined, kinetic energy is the energy of motion. At the microscopic level, it actively opposes structural order, making atoms constantly vibrate and push against their neighbors. When you add heat to a rigid solid, like a block of ice, you are injecting kinetic energy. The atoms vibrate until they break free from their locked geometric grid, causing the material to lose its shape and collapse into a flowing liquid. Increase that kinetic energy further, and the molecules bounce with such force that the liquid bonds shatter. The matter expands outward, becoming a freely moving gas. Yet through all of these phase changes, from solid to liquid to gas, the foundational architecture of the individual atom remains intact. The molecules drift apart, but the core atomic building blocks hold their shape. But there is a thermal limit to that structural integrity. What happens when the kinetic vibration becomes so intense that it surpasses the physical limits of the atom itself? You cross a threshold known as ionization. At thousands of degrees, the thermal vibration becomes extreme enough to strip electrons away from their central nuclei. Ionization produces a superheated, chaotic soup of unbound charged particles, the fourth state of matter, plasma. We see this thermal threshold crossed over our heads during a thunderstorm. A massive electrical discharge superheats the surrounding air, ripping those atmospheric atoms apart to create a momentary flash of plasma. In this state, extreme kinetic energy has dismantled the atomic grid. By breaking the atom into free-floating negative electrons and positive ions, plasma introduces electromagnetic forces into the behavior of the material. Because the particles in a plasma are no longer bound in neutral, balanced atomic structures, the standard rules of thermodynamics can no longer accurately predict how this material will behave. Instead, plasma acts as an electromagnetic fluid. When exposed to an external magnetic field, those chaotic, unbound charged particles instantly snap into alignment, flowing collectively along invisible magnetic lines. While this state of matter is rare on Earth's surface, it is the standard everywhere else. This highly responsive, electrically charged fluid makes up an estimated 99% of all visible matter in the universe. To see this electromagnetic fluid working at scale, you only have to look at a star. A star is essentially a sphere of pure plasma, with its shape and surface flares constantly contorting in reaction to intense internal and external magnetic forces. This creates a physical duality. The universe's most common matter is born from thermal chaos, but its electromagnetic nature forces it into unyielding obedience when it encounters a magnetic field. To harness stellar power on Earth through nuclear fusion, we have to push hydrogen fuel to temperatures exceeding 100 million degrees. The temperature itself presents a structural obstacle. At 100 million degrees, any physical vessel, whether forged from steel, titanium, or carbon, would vaporize upon contact with the fuel. The solution relies on plasma's electromagnetic nature. Through magnetic confinement, engineers use geometry as a trap. A powerful magnetic field suspends the charged plasma in a vacuum. It circulates endlessly in a loop, ensuring heat never touches a physical wall. To contain a material that would vaporize many solid vessels, human engineers had to abandon physical matter entirely. They built a container out of an invisible force field. The specific machine designed to execute this theory is called a Tokamak. It features a toroidal, or donut-shaped, vacuum chamber surrounded by an array of powerful magnetic coils. These circular coils act as a mechanical corset, generating a precise magnetic cage inside the vacuum. The charged plasma is trapped within that invisible architecture, forced into a continuous, frictionless loop. This geometric concept has driven decades of escalating engineering. From the earliest toroidal machines in the 1950s, researchers have steadily scaled up these magnetic cages to hold hotter and denser plasmas. Today, executing this invisible architecture demands some of the most massive industrial construction efforts on the planet, with international projects laying miles of supercooled magnets to trap a single ring of burning plasma. Thermodynamics dismantled the atom into a chaotic storm of raw charge, but strictly unyielding magnetic geometry proved capable of trapping it.